Welcome back. Today's background is the Bill O'Reilly Oval in Whitecliffs, which is in far northwestern New South Wales, almost as far up into the northwestern corner as you can get. And Bill O'Reilly is a fairly famous Australian cricket player from the 1930s, around the era when all of the sort of early theories for quantum mechanics were being come up with. And he was actually born and grew up in this little town of Whitecliffs, and ended up being a very successful Australian bowler. Apparently his best figures were 7 for 54 against England, and he wasn't too unhandy with the bat as well, managing to get a top score of 56 not out. So yeah, interesting place to go. I don't know I'd necessarily want to play cricket on this strip, especially as a fielder, going to chase a ball that's running off to the boundary, but it's kind of cool that you have a town that far out that actually manages to keep a cricket ground going. Okay, so second half of this lecture, I want to start looking at measuring things other than up and down, okay? So what we've done so far is set up a complex vector space for quantum mechanical systems, and we've basically said that the basis vectors for that system will be the measurable states, and all the way through so far we've basically made those basis vectors up and down. And then in the first part of this lecture we basically worked out how to take some arbitrary state and find out the probability that if you do a measurement you'll get an up or a down by projecting that vector onto one of those two basis vectors. The logical question that follows from that is, if you think back to lecture 1, up and down wasn't the only thing we could measure, right? We had this idea that we could take this Stern-Gerlach experiment and it wasn't restricted to having the magnetic field only point in one possible direction. We could point it along X, and we could point it along Y, and we could choose any other direction we like to point that thing. And if our theory is a good theory, our mathematical framework is a good mathematical framework, then we should be able to deal with those possible cases as well, and not just up and down, right? So then the question becomes, well, okay, we've done up and down, how do we deal with right and left in here? And so that's what this lecture's about. Let's get some slides up. What we're going to do here is just think back to real space for a second, right? What we've been thinking about so far is basically just setting our Stern-Gerlach experiment up so that we can measure the projection of the spin, or the component of the angular momentum. I'm going to start using those two terms interchangeably now, because component of the angular momentum is sort of a very first-yearish term. When you start talking about quantum mechanics for a bit, you just basically start talking about spin projections or projections of spins. Okay, they're the same thing. So we've been looking at projection of the spin along the z-axis, but you remember we had these distinct possibilities that we could think about of, you know, along the x-axis is the spin pointing to the left or the right, and, you know, even possibly the y-axis is the spin pointing into the page or out of the page. And so what I want to do in this second half is basically come back and look at how these other two directions fit into our model, and we actually don't have to add anything to our Hilbert space to do these things. All we've got to do is basically see the Hilbert space that we already have from a slightly different perspective. Okay, so what I'm going to do here is I'm going to do it along the x-axis, mostly because I'm a little bit lazy and the x-axis is a lot easier to do. And then I'm going to leave the y-axis to you as an exercise, mostly because you're students and because I'm lazy, I make you do harder work than me, all right? Okay, so let's do this along the x-axis. We can represent any particular spin state for our system as a linear combination of the basis vectors up and down, right? If we've got a real, proper, sensible theory here that covers all the possible directions that a spin can point in, then, you know, we should be able to take left and right, and if they exist in that vector space, which they must, if it's going to work properly, we must be able to write them as linear combinations of the basis vectors. And those basis vectors at the moment, there's only two of them. There's up and down, right? So what we can do is set up to do that. And the way we would do that is basically to go, what do we know about left and right that will maybe give us a clue for how to write those two things as a linear combination of up and down, right? There's no other better way to do it than to just work on an educated guess. And quite a lot in physics, we actually do this, especially if you're coming up with new theories. You often just go out on a limb, make an educated guess and hope that it works. And this is one of those educated guesses that happen to work, so it ends up in a textbook rather than in a garbage bin, all right? So one thing that we know here is that if we prepare a spin pointing to the right, and we saw this in the first lecture, and we measure the projection of the spin along Z, we will get either a 50% chance of it pointing up or a 50% chance of it pointing down, right? So what that means is that we know that the probability of up is a half, the probability of down is a half, and if we think in terms of sort of the arbitrary state vector that's described by alpha u and alpha d in the first half of the talk, what that means is alpha u conjugate is equal to a half, and alpha d conjugate is equal to a half as well, right? If we think about it like that, then basically what we would do is it's going to be something times its complex conjugate is equal to a half, and the best thing we can think of that when you multiply it by its complex conjugate is equal to a half is 1 over root 2, right? 1 over root 2's conjugate is 1 over root 2. You multiply 1 over root 2 with itself and you get a half. So the obvious thing to write here for a vector that's pointing to the right as a sort of possibility for what that vector would be is as 1 over root 2 up plus 1 over root 2 down, okay? Fairly simple linear combination of up and down that gives you a 50-50 probability of getting an up or a down from a measurement, okay? So let's just take that as a possible expression for right, okay? And it turns out that it is the expression for right, but let's just take it as that. You would then go, well, now we want left, right? And we remember if we have a vector pointing to the left, then, you know, it's got a 50% probability of pointing up and a 50% probability of pointing down. So you would sort of start from the same position of going, well, hang on, I should have a 50-50 probability for up and down, so why isn't left exactly the same? 1 over root 2 up plus 1 over root 2 down, okay? We know that they can't be the same thing, right? Something pointing to the left is not equivalent to something pointing to the right. So there's a problem here. And so the question becomes, well, what else can we use that we know that we can use to lock down what our L vector would be? Now, if we think about it from a measurement perspective, we know that right and left are two distinct measurable outcomes, right? If we ask what the projection of the spin is along the x-axis, then we know that it's either going to point to the right or it's going to point to the left. Those are the two possible outcomes, okay? And that means that if we were trying to build a Hilbert space off those, the right vector would be perpendicular or orthogonal to the left vector, right? So what we know is we have a form for the right vector. What we need to do is come up with a form for the left vector that still gives us the 50-50 probability, but is orthogonal to right, okay? And if we think about this a little bit, there's actually a really good option for that, which is that what we can do here is try and find the vector such that the inner product of left and right will be equal to 0, and it meets the requirements for the probabilities being a half for up and a half for down. And so one educated guess that we can take for that would be maybe left is actually up minus down instead of up plus down, okay? That would give us a vector that instead of going diagonally upwards because it's sort of up plus down, would point diagonally downwards because it's up plus minus down. And so downwards diagonal is orthogonal to upwards diagonal, right? That would be our educated guess because it's just a clever little piece of geometry. We can check it really quickly. So our right vector here, let's write it as a column vector, would be 1 on root 2, 1 on root 2. And so this is something as students you should get really good at as well, being able to translate expressions like this directly over to column vectors, or taking column vectors and converting them back into expressions like this. Okay, it's a really handy skill to have when you're learning quantum mechanics. And of course our left vector here would be now 1 over root 2 and minus 1 over root 2, like so. Okay, and of course here what we want to get, I could toss a coin in the air and choose one. Maybe what I'll do is the one with the left as the bra here. So let's do left, right. And I'll let you do right, left for yourselves just for practice and to confirm that this all works properly. Okay, so this would now be 1 over root 2 conjugate minus 1 over root 2 conjugate. And right is now our column vector, 1 over root 2, 1 over root 2, like so. And if we multiply these together, of course, we know that the conjugate of 1 over root 2 is 1 over root 2, and the conjugate of minus 1 over root 2 is just minus 1 over root 2. So what we would have here is 1 on root 2 times 1 on root 2, which is the 1 on the left times the 1 on the top, plus, actually, that's going to be a minus 1 on root 2, 1 on root 2. And I highly advise this in exams as well. Think your way through while you're doing the maths and try to catch yourself making mistakes. I make stacks of mistakes all the way through just everything, including lectures, and just catch them on the way through. It's most of the way I stay out of trouble when I'm having to do things, is not because the errors slip, but because I catch them on the way through and fix them. Okay, just like that one being a plus should have been a minus. So this is now a half minus a half, and of course a half minus a half is 0. Okay, so those two vectors are orthogonal. It's pretty easy to check orthogonality. And you'll remember that I pointed out in the last lecture, you know, this is actually orthogonality in particular is a useful thing to be able to check at various points very, very quickly by doing inner products. Okay, so make sure you know how to do that. All right, so now we can take a figure that you will have seen in the last lecture and actually spice it out a little more with some detail. So you'll remember we had this sort of Hilbert space diagram in the last lecture where we had our up and down as our orthogonal basis here. And then we had two vectors that were in green and orange that we just called chi-s and chi-s because they were, you know, two sort of symmetric states between up and down. And what we can see here now, working off the maths that we've just done, is that these two vectors here are actually left and right, right? They're sitting right there in front of you in that Hilbert space. It's not like we have to add anything to it to get them in. They're there, just waiting for you to use. The problem is that they're not the basis vectors at the moment, right? They meet all the requirements for a basis. They have unit length, both of them, and they're orthogonal to each other, but at the moment we're not considering them the basis. Okay, so how do we switch now from a measurement of the spin along z to a measurement of the spin along x? All we do is we take our Hilbert space and we rotate everything in it by 45 degrees, right? Or the other way of thinking about this is just leaving the Hilbert space alone and taking your perspective of what the basis vectors are and just, you know, tipping your head on its side by 45 degrees and going, oh, hey, now I'm going to consider this to be my basis, right? And so now what we've got here is, in principle, we have a basis that is the right and the left. They're now our linearly independent basis vectors. They're the things that we would measure in a measurement of what the spin's projection along the x-axis is. And up and down can be written as linear combinations of left and right. Okay, I'm not going to do it here because it takes a little bit long, and for some of you it's kind of obvious. And actually, it's better that you do it for yourself than I do it and you watch. So what I'm going to get you to do as an exercise outside of here is actually try to write up and down as linear combinations of left and right. There's two ways to do it. One is to go through the same line of argument that I made on the two slides earlier where I got right and left. The other way to do it is just to take these two basis vectors and rearrange them so that you've got up with left and right and down with left and right in it, okay? I'm going to encourage you to do both because, again, in whether it's physics or maths or whatever, the more problems you do for yourself, the better you get at the subject. And so if you can do both ways of solving that problem, then you'll understand the problem a little bit better than if you just do one of them, okay? So I'm going to let you do that for yourself. Okay. The place where this gets interesting is if you now start to think along the y-axis, and you can actually run the same line of logic as we did for getting from up and down to left and right, and the same logic you could use to go back again from left and right to up and down to build yourself out into a basis of in and out, okay? And the tricks here basically are that if you have a spin that's pointing out and you ask whether it's up or down, you'll get a 50-50 probability, right? So that would be this expression here. We're basically saying if we've got a state that's where the spin is pointing out of the page and we want to measure what its projection is into the up state, that would be a probability of half. Out to down will be a half. Into the page to up will be a half. Into the page to down will be a half. And likewise, you can build a whole pile of these relations for taking the in and the out state, not to the up and down, but to the left and right, okay? So you can see here there's a whole pile of possible things that you know as sort of projections have to give you probabilities of a half. The other thing that you know in here must be true is that the in and the out state have to be orthogonal to each other, right? They're distinctly different measurable outcomes of making the measurement of is the spin aligned along the y direction, right? It'd be like taking our Stern-Gerlach experiment and rigging it up so the field runs along y. If you build all these together, and it's actually one of the tutorial questions. So some of you now will have seen that there's a nice big list of 20 tutorial questions up on the website. This, I think, is either question 1 or question 2, is actually to go through and build out what these two vectors look like and some of the relationships that come about in doing this. It's actually kind of a complex problem getting in and out. And the reason why getting in and out is a complex problem is because you start suddenly getting complex amplitudes. Okay, so if you do this, these are the answers you get. You get in as a linear combination of up and down, except now instead of having 1 over root 2 and 1 over root 2, what you have is 1 over root 2 and I over root 2, right? And out ends up being the sign reversed linear combination for that, so it's basically 1 over root 2 and minus I over root 2. Now what you've got is a vector that's very hard to draw on a page in any other basis than out and in being the actual two basis vectors, right? If you try to draw it in a basis of up and down and left and right, if you can draw it, come and show me, because it'd be kind of cool. I've tried many times to see, in my head what this would look like. Can't do it, okay? So, but in much the same way, those two vectors exist in the full 2D complex vector space in here. They're just in such a way that we can't draw them in that page. And all we'd have to do to adjust to that measurement is to basically, again, take every vector in the entire Hilbert space and just rotate the whole space round till those become the basis vectors, and then do projections onto that basis, right? And then at that point, up, down, left, and right would be pointing in directions that we couldn't draw if we happen to have, for example, O and I running along these two axes. We wouldn't be able to draw the other ones because they would have complex components. And if you want a really advanced problem, you can convince yourself that you can write L and R and U and D as linear combinations of O and I, and you will find that you get complex amplitudes when you do that, okay? That is a tough exercise. But ultimately, the really key point in this is that everything that we need to deal with our quantum spin problem is already built into this 2D complex vector space we started with. It's just that up until this half of the lecture, we just didn't see it because we weren't seeing where those vectors were in that space, okay? Completely interchangeable. And just to highlight a point, really changing this idea of changing basis, of going from one interesting measurement, you know, for example, projection along X to projection along Y, is really just a rotation, okay? In this particular case, it's a rotation of 45 degrees, which is half of 90 degrees. And if you stay around in quantum mechanics long enough, you'll find out that there's an operator for doing this, which is really just a matrix. And those of you who've done a little bit more maths than others will know that you can rotate vectors by using matrices, okay? They're called rotation matrices. And this is exactly what goes on here. If you want to change from one basis to another, the way you implement a change in basis is you basically have a matrix operator, and that matrix operator is just a rotation matrix, and just switches you from one basis to another, and then you start calculating probabilities of outcomes in whatever new basis it is that you're interested in measuring. A lot of the books make it look a lot more complicated than that, but bases are really quite simple once you see it from that perspective. Okay, so there's two more things I want to get to before we finish for the day. One is, and because it's got 2 stars at the top, it's a quite an advanced point. So I don't consider this one to be examinable. It's more there because I know that in every particular class, there's students who kind of want to really push themselves on the ideas here. One thing that comes from what we just saw in terms of bases, vectors, and projections and so forth is there's ultimately an underpinning concept that's known as phase ambiguity. What that means is that the only thing that really matters in quantum mechanics is the relative phase between 2 vectors, and not the absolute phase of a vector, okay? The best way to think about this is if you go right back to the first half of this lecture, we had our chi-s and our u, right? And anything that comes out in terms of, you know, calculating probabilities, because that's really, you know, everything in quantum mechanics is either measurable outcomes, which are your basis states, or the probability of measuring something, which is what comes out of projections, right? They all rely on an inner product, which is really just a relative angle between 2 vectors, right? A dot product is really just scaling the lengths, but the length's a unit, and the cos of the angle in between. So it's really just the relative angle, relative phase between 2 vectors that matters, right? Where that chi-s points in as an absolute direction is entirely irrelevant, because the only time you're ever going to use it is by projecting it onto a basis vector in order to get a probability, okay? So the only thing that ever matters is relative phases, and we've now got enough maths to actually test this. So I'm going to let interested students do this on their own, because I would spend a whole hour of separate lecture going through the maths for this. It is kind of cool. I will have the worked example for this in the reference notes for my notes on the website. So if you decide to have a crack at this problem, you'll have a solution you can work through. And so there's 2 things that you can show in here. One is that you can take some arbitrary state A, it would be like our chi-s, and what you can do is multiply it by an arbitrary phase factor, right? If you think about what an arbitrary phase factor is, really it's just rotating a vector by some angle in the space. And what you'll find is that it doesn't change the probability of measured outcomes. And the reason for that is that when you take the conjugate to that measurement, you're actually then introducing a phase factor of E minus I phi. And as you know from, Euler's theorem, how do I used to remember this? Old MacDonald has a farm, EIEIO, and I used to remember it as EI theta, EI minus theta equals 1. Old MacDonald had a 1, EI equals 1, okay? Little mnemonics for measuring things. So that's the first one. And then the second one, what you can do is you can take 2 basis vectors and you can multiply them by an arbitrary phase factor and show that they still remain orthogonal, okay? Kind of an advanced point, so I don't want to go into it too much, but I know some students are always looking for a little bit extra to have a play with, and so I'll let you have a go with that, and if you want, you can discuss it with me separately outside of lectures. Okay, so that's the first point. The second point I want to come back to is more of a warning about some of the trouble that you can get into at around about this time in a quantum mechanics course like this. And it's basically a problem that looks a little bit like this. PHYS2111 student comes in, he starts learning about 2D Hilbert spaces, starts looking on the internet for, oh yeah, let me look up this, that, and the other thing, and all of a sudden finds a thing called the Bloch sphere. If I was teaching this subject 20 years ago, I absolutely wouldn't have this problem. The problem has come about for two reasons. One, we have the internet now. The other is that we have quantum computing. And quantum computing is one place where actually you really like to think about things sometimes in terms of this thing that we call a Bloch sphere. The reason why that thing comes about is exactly the problem I've been talking about for the last two lectures of this struggle to visualize what the vector spaces look like in quantum mechanics. So here we go. Here's a Bloch sphere. It's very highlighted note as best I can do. It is not a proper vector space, okay? The reason why you can tell that it is not a proper vector space is that none of the basis vectors in here are orthogonal to each other. So for example, up and down are at 180 degrees. They're not at 90 degrees. That means it's not a proper Hilbert space. It means that if you try to do quantum mechanics in this space, it's not going to work. The reason this space exists is because trying to take a 2D complex vector space and represent it on a 2D page is quite limiting, and we've seen that this lecture in the sense that we can do right and left and up and down, and then all of a sudden, as soon as we get anything with a complex amplitude, things get rather difficult, okay? The way this diagram cheats is that, well, it's not even a cheat. What's going on here is that you're adding a third dimension, right? And so now you've kind of got a 3D space available to try and represent a 2D complex vector space rather than a 2D real vector space to represent a 2D complex vector space. It means that you can fit more of the possible vectors that you will get in that 2D complex vector space into the space that you represent on the page. And in particular, this way of representing it enables you to get all of the possible basis vectors to show up in one diagram. So you've got up, you've got down, and if you look at in the plane, you've got left and right, and you've got in and out, okay? So this is nice because you can kind of see more of your Hilbert space. And when I say more of your Hilbert space, basically what I mean is you kind of distort it so that you can get more of the vectors into it. The compromise that you have to make in order to get this is that your measurables are no longer orthogonal vectors, which means that you've got to be very careful about how you think about it in terms of things in here, right? And it can very easily lead you into some dangerous misconceptions, one of which I'm just going to very quickly prove to be the case now, okay? So imagine you're looking at Bloch spheres, and this is the reason why I warn you about it, because if I don't warn you about it, there'll be a lot of undergrads who will go off and start to go, oh, you know, maybe up is orthogonal to left because there's this diagram on the internet where I can see up is orthogonal to left, right? As undergraduates, you should be critical thinkers, which means you should know full well that you never trust anything on the internet, at least without being able to verify it. Actually, I wouldn't even trust me on the internet without being able to verify it. And this is why I'm going to verify it now, right? I'm going to prove to you that up is not orthogonal to left. So let's do this as a quick little exercise here. If up was orthogonal to left, we should be able to write up left as an inner product and get the answer to be 0. Okay, so let's do this. I'm going to speed up now because we're kind of used to this. Up as a ket is basically 1, 0 row vector. We got left earlier in the lecture, it's 1 over root 2 up minus 1 over root 2 down. So it's now going to be a column vector, 1 on root 2 minus 1 on root 2. And then we just multiply this out, right? So 1 times 1 over root 2 is 1 over root 2. 0 times minus 1 over root 2 is 0, plus 0. Add those two things together, we get 1 on root 2. Notably, we don't get 0. Okay, so up is not orthogonal to left like it looks in a Bloch sphere. And the reason why this is misleading you is because it's not a Hilbert space, it's a Bloch sphere. It's a different representation. That said, Bloch spheres are very, very useful. And if you go on to do courses in quantum computing, you will actually start to use them probably even more than you do Hilbert spaces. And the main reason is that once you get beyond simple 2D problems, it gets very hard to visualize Hilbert spaces, so you just don't, and you just let the mathematics roll, and then you use your Bloch spheres to try and visualize things, right? So you can imagine here, for example, taking a spin that you start in an up state, and if you do quantum computing courses, you'll learn about this sort of thing. Start with spin in an up state, then you do something that maybe tips it into the plane, so it's, you know, able to move, and then you might give it a kick so that it can rotate around through, you know, left and right states. And then, you know, it might go off into some arbitrary place, and then you'll do a projective measurement back onto one particular axis to get back whether you've got a qubit of 1 or a qubit of 0, which would correspond to an up or a down. Okay, so this thing's really useful in terms of working out how to manipulate quantum bits, or, you know, quantum spin systems for information perspective. But you should be very cautious in using it because it can walk you into some traps. Okay, so I think I'll finish this lecture there, and what we're going to come back for in lecture 4 will be operators, matrices, and expectation values. I'll see you then.